All right, here we go again. Let's look at some problems in Chapter 6. So we're going to be looking at Chapter 6, and we're on page 194. And we're going to look at problem number 24 to start with. Okay, you throw a 3 Newton rock vertically into the air from ground level. Okay, so we're sitting here and we throw a rock up. There's the rock. And the weight of the rock is 3 newtons, 3.00 newtons, 3 sig figs. That's the weight of the rock. That's a W, by the way, rock. Okay. You observe that when it is 15 meters above the ground, it is traveling at 25 meters per second. So when this is 15 meters, and if you want to write it this way, let me write weight over here. Weight of the rock is 3.00 newtons. And when the y is 15 meters, oh me, it is traveling at 25 meters per second. Its velocity is 25 meters per second, okay? And that's at 15 meters, okay? That's an arrow pointing up. Use the work kinetic energy theorem to find the rock speed just as it left the ground, okay? So at 15 meters, it's this speed, and so we could call that final. We want to find the initial velocity just as it leaves the ground or leaves the person's hand. Okay, and again, we're assuming that he's put his hand on the ground and threw it up. Okay, so we got to find initial velocity. So we're looking for A, 24A. What is its initial velocity just as it left the ground? Now, we want to use the work kinetic energy theorem, correct? Yes, we do. Now, the work kinetic energy theorem says what? That mgh is equal to 1/2 mv squared final minus 1/2 mv squared initial. All right. In other words, the change in potential energy is equal to the change in kinetic energy using the work kinetic energy theorem. All right, now there's one thing I did not do here. Notice this is mgh, and mgh is positive only when it's falling down. So since the rock is going upward, it has to be negative, okay? Because it's going upward, it's going against gravity, so therefore the work done by gravity is negative, okay? Does that make sense? It has to be negative because kinetic energy and potential energy can't be the same when the rock's going up. Kinetic energy is positive going up, and the potential energy, gravitational potential energy, has to be negative, y'all. It has to be, all right? So what we're going to do then is we are going to do what? We are going to solve for we want to solve for the initial velocity. Well, how in the world do we do that, Mr. Shields? Well, okay, here it is. So let's write the equation this way. We're going to solve for initial velocity. But first thing I want to do is just isolate the initial velocity by doing what? Subtracting 1/2 mv squared final from both sides. So it's going to look like this. Negative 1/2 mv squared initial is equal to negative mgh minus, because I'm going to subtract this from both sides, 1/2 mv squared final, okay? So we're going to do that. Now let's do something else. Let's get rid of the, let's see here now, before I get too far ahead of myself. We can multiply, let's see, if we multiply both sides by 2, That would be a good thing to do. Let's multiply both sides by 2 to get rid of the halves. So if you do that times 2 and this times 2, you get what? You get mv squared initial is equal to 2mgh, negative by the way, minus, and that's minus, don't let me forget it, mv squared final. Okay, so now we got rid of the halves, all right? That's important. Now let's get rid of the mass, so divide everything by m. And we get what? We get a negative v initial squared is equal to negative 2gh minus v final squared, right? Okay? Because really what you could do is factor the mass out. You say, oh, no, wait a minute, that's two different. Put parentheses around gh minus v final squared and pull the m out because the mass is the same. Yes, that is correct, okay? So, yeah, I know there's an m here and an m there, but you can actually factor it out and there's 1. So it cancels out, okay? So you cancel everything out. Now, notice everything's negative. So what I can do is multiply everything through by negative, and it becomes positive, right? So multiply both sides by -1, and we get what? V initial squared is equal to 2gh plus what? Well, good heavens, I can't even think. V final squared, right? You say, Miss Shields, why did you do all that? Well, because you got to do the physics before you do the math. All right, multiply both sides by -1. And there you go. Now we can solve for it. It's not quite simplified. Take square root of both sides. So we got V initial is equal to the square root of 2gh plus V final squared. Okay? Now we can plug everything in. Now the physics is done. We're done with the physics. We're done. So we say V initial is equal to the square root of 2 times, and oh, what do I put in here? Do I put a negative? No. Because you say, well, how do you know that? Because the rock's going up, it's not going down. So it's going in the opposite direction. Okay? So there again, you gotta watch your physics. All right? And then the height is what? 15 meters? Yeah. And this is all on the radical plus. And that is what? Was it 25? Let me just look at my notes, crazy, and I'll have it. Yeah, 25. Yeah, 25 meters per second. And then square that. Okay? And you say, well, now how do you know that's right? Well, because it's going up. How do you know the 25 is supposed to be positive? Because it's going up. Okay? Everything's going up. So everything's positive. Okay? Everything's positive. And notice how everything worked out to be positive. Well, isn't that something? Okay. Now, the initial then is equal to what? Oh, Lord, I got all this writing on here and scribbling. 30.3 meters per second. There you go. So that means, now does that make physical sense? Well, sure it does. Well, it's more than the velocity at 15 meters. Well, it's supposed to be. Because it's the initial release. The rock is slowing as it's going up because it eventually reaches 0. At maximum height, it reaches 0. Okay? And see, that 3 newtons threw you, didn't it? You know, we're going to need that? No, we don't need it. Isn't that something? Okay? Because remember, y'all, the effect of gravity is not dependent on the mass of the object. Notice how the mass canceled out, y'all. Well, why? Because gravity, the acceleration that's at work here, is not dependent on the object's mass. It's not dependent on the object's mass. Okay? And we see that in our equations. It canceled out. All right, now, so there's part A. Now let's look at part B. So 24B says what? What is its maximum height? Okay? What is its maximum height? Well, now let's remember, y'all, that the acceleration is constant. How do you know that, Miss Shields? Because the only acceleration on the object is gravity. Yeah, but what about when he threw it out of his hand? When it leaves his hand or her hand, when it leaves the hand, then the only thing that's affecting it is the acceleration of gravity. And, of course, air resistance, but we're neglecting that here. Okay? That's it. That is it. So the acceleration is constant. All right? So, that being said, here comes that equation again that I told you we'd use a lot that becomes very useful. 2g delta y. There we go. And solve for y, which is height. If you want to put h there, okay, put h. H and y, same direction. Height is in the y direction, okay? So then y becomes what? Change in y equals what? Well, you got v final squared minus v initial squared over 2g. And so y then becomes what? V final squared, which was 0 meters per second. And you say, what is its maximum height? I didn't write that down, didn't I? What is the final velocity in the y direction? It's 0 meters per second. I forgot to write that down. Sorry about that. Okay? Yeah. Oh, and I forgot something else too. That's supposed to be negative. Yeah. All right. Okay, now watch. You better pay close attention to what I'm fixing to do. Okay, so let me read it again. It says, what is this maximum height? Well, at maximum height, this is max, 0 meters per second. So we plug in 0 meters per second squared. I don't even need to put that, but I will. Now watch very closely what I'm fixing to do. That's not negative. It's this right here. 30.3, right, meters per second. That was the initial. Squared over 2 times, not negative 2 now, not negative 9.8. The negative's already there. See, look, negative is already there. It's already there. I don't need to put it again. Meters per second squared times, yeah, that's it. I'm sorry. I'm getting ahead of myself here. So when we square that, it is negative. We don't square the negative. We square the value and then put the negative on it. Well, hello. Negative divided by negative is positive. So we get an answer of 46.8 meters. Now, does that make physical sense? Well, of course it does, because it's going up. Okay, it's going up. So you should get a positive y answer, 46.8 meters. It's going up. All right, great. All right, that's number 24. Let's look at number 32. I think I'm just going to work most of these even-numbered problems here. All right, let's look at this. To stretch an ideal spring 3 centimeters from its unstretched length, 12 joules of work must be done. Okay, so we got a spring here. And we're going to stretch it from here to there. That distance right there, that change in y, is 3 centimeters. Is that what it says? Yeah, 3.00 centimeters, which is equal to 0.03 meters. You always put it in meters, guys. Maybe decimal 2 places left. And it takes, to do this, it takes 12.0 joules of work. What is the force constant of this spring? So we first thing, and this is 32A, first thing we got to do is do what? We got to find what is K. Okay. What is K? Well, y'all, that's easy. We know by definition that the work done on a spring is equal to, and you could also put a U elastic there, or U spring, is equal to 1/2 kx squared. Or y, that can be y, k, or 1/2 ky squared, since we're going up and down. It didn't tell us we were going up and down, I don't think. But I like to do it that way. You could do it horizontally, same difference, okay, because the spring constant is the spring constant. Now, all right. So let's solve for this. So we're going to solve for K, which is equal to the work done on the spring, divided by what? Oh, me. That becomes what? That's 2 times the work divided by what? Y squared, is that correct? Yeah, y squared, y final squared, or delta y final, or we can say delta y, either way, okay, final y. So plug everything in, 2 times 12.0 joules divided by what? It was 0.03 meters squared, and you get what? Man, I'm having a hard time reading this. 2.67 times 10 to the fourth, 2.67 times 10 to the fourth newtons per meter. That's your spring constant, your K constant. Now let me double check that, because when you square 0.03, all right, so 24 divided by 0.03 squared, yeah, 2.67 times 10 to the fourth. Yeah, that's correct. Newtons per meter. Then let's look at 32b. 32b says, what magnitude force is needed to stretch the spring 3 centimeters from its unstretched length? Okay, so we want to know then how much force. We want to know the force of the spring. So we want to know what force is required right here. Well, y'all, that's Hooke's law. Force of the spring is equal to negative kx, right? Negative kx. And if you want to, you can just leave it positive. So let's just leave it positive. I know that it's going in the negative direction, but what we could do is the negative times negative be positive, okay? Since it's going below y, okay. Cancel that out. All right. Or it would tell it. Let me read that again. It would tell us that, yeah, what magnitude force is needed to stretch the spring. Yeah, okay. Remember, the negative tells us that there's a restoring force in the opposite direction. That's the only thing the negative tells us, okay? So to pull the spring down, it would be a negative force, okay? Now, I'm not sure. I'm pretty sure. Well, yeah, I am sure too. When you enter this in your quizzes, make sure you put positive. They made everything positive. They worked this problem with it laying down on a horizontal plane. I didn't work it that way, okay? All right, so we take our spring constant, 2.67 times 10 to the fourth newtons per meter, times 0.03 meters, and you get an answer of 801 right at it newtons, okay? So there's the force of the spring constant. And then it says what? How much work must be done to compress the spring 4 centimeters from its unstretched length? And what force is needed to compress it this distance? So we got a couple of work here, okay? All right, so 32C, you actually got 2 things to do. So instead of stretching it, we are doing what? We are compressing it. Okay, so it's here now, and it was ... I should have made all that dots, okay? So now this distance is 4 centimeters, or 0.04 meters. So that's y. Okay. All right, well, it says how much work. Well, we know the work done on the spring is equal to 1/2 k, and I'm going to use y squared. Okay, and that can be changing y, and so the work then is 1/2 times the spring constant. Y'all, that doesn't change, times 10 to the fourth newtons per meter, times 0.04 meters, and you get an answer of 21.36 joules. So we get 21.36 joules. Let me write that again. The work is 21.36 joules, or you could say 4. All right, now how much force is required to do this? Well, we worked the same problem, y'all, just like we did in part B. Force of the spring is Kx, or Ky, And so we do what? 2.67 times 10 to the fourth newtons per meter times 0.04 meters. And we get an answer of 1068 newtons. Okay, there we go. There's that answer, and there's that answer. 1068 newtons. All right, that's a good problem too. I really like that problem. All right, let's move on. Let's look at number 52. Yeah, number 52. Okay, so this is 52 on page 196. Yeah, 190. Darn it. 96. Clear that off. I hate that when I do that. All right. Number 52 says when it's 75 kilowatts or 100 horsepower engine is generating full power, a small single engine airplane with mass 700 kilograms gains altitude at a rate of, oh my stars, at a rate of 2.5 meters per second. What fraction of the engine power is being used to make the airplane climb? And then it tells you the remainder is used to overcome the air resistance and the inefficiencies in the propeller and engine. All right. Okay, so really what this is a ratio problem, all right? So notice we got an airplane, and so the airplane is climbing. I don't know if I can draw this or not. There's the airplane, and the airplane's climbing, okay? And the mass of the airplane is 700 kilograms. I believe that's right. Yeah. And the power of the engine is a 75 kilowatt. That's 75,000 watts. That's the power of the engine. Okay. And it says it gains altitude at a rate of 2.5 meters per second. So that means that the velocity of it increasing altitude is 2.5 meters per second, and that's the velocity to gain altitude. Okay, what fraction of the engine power is being used to make it climb? All right, well, let's look at this then. Well, first thing we need to do is determine the power of the engine at the power of the engine at 2.5 meters per second, at the rate of 2.5 meters per second velocity increasing in altitude. Well, now I didn't draw, I know I drew that at an angle and I probably should have drawn it straight up, and that's okay. So we know that gravity, we know that mg, that weight, is affecting the rate of climb, right? So the airplane is going up, gravity is pulling down. So the only force that besides air resistance, and we're negating that on this calculation, we're saying that everything else is going to be used up by air resistance and inefficiencies and so forth, okay? So let's find the power at this rate. Well, we know that power can be found a couple of different ways: work divided by the time, or the force times the velocity. Now remember, this is power. Power is the derivative of work with respect to time, so it's a derivative. We're looking at rate because it's a rate problem, but we don't have a function, and we're looking at everything as it being constant, okay? So we just plug everything in. How do we find the force? Well, the force of it climbing upward is the same as the weight of the plane, okay? So we say then we have 700 kilograms times 9.8 meters per second squared, and it has to be positive because it's going up, not down. It's going up, all right? 9.8 meters per second squared times then the velocity, 2.5 meters per second. And we get an answer of 1.71 times 10 to the 4th watts. Okay? So that is the power at that rate. Okay? That is the power at that rate. And it asks, what is the percentage? All right, read it again. It says, what fraction of the engine power is being used to make the airplane climb? So we know that the power of the engine, maximum power is 75 kilowatts, okay? Well, then that's a ratio, isn't it? So we're going to look at doing this right here, 1.7 times 10 to the 4th watts divided by 75,000 watts, or 75 kilowatts, okay? And this is times 100. And so we get what? 23%. Okay, so it's using 23% of the engine power, because that's what it's asking. What fraction of the engine power is being used to make it climb? So it's not using a whole lot of the engine power to climb. 23%. Everything else is being used to overcome all those other obstacles that was mentioned, okay? So that's number 52. All right, students, now let's look at number 56 on the same page. As you're applying a constant horizontal force, and it gives you the function there, to a what? To a crate sliding on a factory floor. So we got a crate sliding on a factory floor. All right. And the force is, is that a negative? Yeah. Negative 8.00 newtons. I, caret cap, plus 3 newtons J, caret cap. Okay? So that's the force that's being applied, and that's a vector, of course. Okay? At the instant that the velocity rate of the crate is, so now we're looking at the velocity of the crate at the instant, 3.20 meters per second I plus 2.20 meters per second J, and put the caret cap on it. What is the instantaneous power supplied by this force? So we want to know what the power, the instantaneous power is, okay, by this force. All right, well, we know that by definition power is the derivative of work with respect to time, but notice it's already given us the unit vector notation. So power can be found this way. We can say the power of the x component, or I component, I, plus the power of the y component, or the j component. And remember how we find power. Power is found by saying the force times the velocity. So we have a force, and we have force components and velocity components. So you say, don't we have to do a derivative? No, we don't need to do a derivative. First of all, it doesn't give us a time. So how are we going to take the derivative with respect to time when there's no time in our equation? But we do have the components, and by definition, power can also be found by taking the product of the force and the velocity of the object during the applied force. So we have components. So we have a negative 8.00 newtons I times a positive 3.20 meters per second I, caret cap, plus my J component of my force is 3.00 newtons J, times my J component of my velocity is 2.20 meters per second J. And so we get a total power, or we get the instantaneous power, at that given instant to be what? The instantaneous power is what? It's going to be a negative 19 watts. Negative 19 watts. How's it negative? Because 8 times this, 8 times 3.2 is 25, negative 25.6, and 3 times 2.2 is positive 6, okay? All right. So we get a negative 19 watts. So what does that mean? All right. What it's telling us then is that the x component of the force is opposing the x component of the velocity, so it is opposing the motion of the crate. That's what that tells us, okay? It tells us that it is opposing, that the x component is opposing the motion of the, or excuse me, not the x component of velocity, but the y component of velocity, okay? It is opposing the motion of the crate. All right? It's opposing it. That's what it tells us. All right, let's move on to number 64. '64 is a little bit lengthy, but we'll get through it. Okay, 64, and this is on page, same page, 196. 64, we have a 5 kilogram package slides 2.8 meters down a long ramp that is inclined at 24 degrees below the horizontal. So let's draw the horizontal. It's doing this right here. This angle right here is 24 degrees. There's the crate. The mass of the crate is, or package, sliding is 5.00 kilograms. Of course, we got G, which is negative 9.8 meters per second squared. Okay. All right. Now, okay. And it slides 2.8 meters down a long ramp that's inclined. So from here to here, this is 2.8 meters, and that would be the change in x. Okay, you say, now wait a minute, there's x. You got to remember now, it's in relation to which way the object is sliding. So this becomes our x. Remember, x is just a displacement anyway, so 2.8 meters. Okay, below the horizontal. The coefficient of kinetic friction between the package and the ramp is mu of k, so the coefficient of kinetic friction is 0.310. I think that's right. Yeah, calculate the work done by the package, work done on the package by friction. Okay, so we're going to calculate the work done by friction. Well, here again now, we've got to remember what friction is. Okay, and what is friction? Well, we got to draw all our vectors, don't we? We're not through with our diagram, are we? So let's do that. Let's do that. And we have, of course, the normal force is this way. Remember that we've got a force in the opposite direction. If it's on a flat surface, that'd be weight, but we know that we've got to think about the angle first. And it is sliding that way. And if you remember, this is mg sine theta. This is the component of the work done by gravity. And by the way, the friction is in the opposite direction. So friction, shoot, I meant to draw that straight. Got to be careful now, not erase everything. So the friction is this direction, okay? That is friction right there. Friction is going to be going up the incline because the box is sliding down the incline, okay? All right, and the force that's causing that is gravity, and that is, right here is gravity. So this is mg, that's mg sine theta. Remember when we talked about this the other day when I was working a problem, that the box does not sink into the incline. It has to follow the shape or the angle of the incline. So the effect of gravity on the box or crate is affected by the angle of the incline. It can't go straight down because the incline stops it from going straight down, so therefore it has to go at this angle. And that is the component of the object's weight. Okay, that equation right there is the component of the object's weight. So what is this? Well, if you remember, friction, mu k, is equal to what? Mu mg, isn't it? Mu of k mg. Well, where's that on our problem? Well, mg here, mu of k times the normal force, right? So where's my normal force? Well, here, but this, remember, these are equal. Remember, the normal force up is equal to the weight going down, and it's straight down. It's not this way, it's this way. So this then becomes what? Well, this is opposite over hypotenuse, which is sine. This is adjacent over hypotenuse, so this is mg cosine of theta. That right there is my friction. So now we can find the work done by the friction. Okay? The work done by the friction. So, let's look at this now. So the work done by friction is equal to what? Well, the work done by friction, remember work is equal to what? Well, work is equal to the force dot product S. So where's our force coming in? Well, where is it coming in? Well, it's coming in with what? It's mu of k mg cosine of theta times S, right? It sure is. So now let's plug everything in. So the work done by friction is equal to 0.310, yeah, times the mass, which is 5 kilograms, times gravity, which is 9.8 meters per second squared, times distance, which is 2.8 meters. Okay. The work done by friction. Now, we got to look at our angle. I forgot my angle here. I didn't put the angle in. I'm going to put it in right now. Cosine, is it 24 or is it 360 minus 24? 336. Well, let's see. If we say 0.310 times 5 times 9.8 times 2.8 times the cosine of, what did I say? 336, yeah. What do we get? We get 38.85. Okay, so we get 38.85 joules. So I could have used 24 or 336. Why did I use 336? Because look, if you go all the way around this way, it's a 336 degree angle. It's in the fourth quadrant. All right. Now, is the work done by friction positive or negative? Well, it has to be negative, y'all. It has to be opposing the work done by gravity. Okay? It has to be. So it has to be negative. There again, there's where the physics comes in, and that was what, 64A? All right, now let's look at 64B. The work done on the package by gravity. Okay, well, the work done by gravity. Well, let's look at that then. Okay, so 64B. And y'all, we've already got the equation. Look right here. Remember I told you, oh, but the gravity's pulling straight down. Yeah, but y'all, it's not going down. It's not going that way. It's going this way. And so where's my component of gravity, the work done by gravity, or the work done by the weight? It has to go this way, and that's opposite over hypotenuse, which is sine. So then the work done by gravity is equal to what? Mg, goodness gracious, sine of theta dot S. And so when we plug all that in, we've got 5 kilograms times 9.8 meters per second squared times sine of, and what angle do we use? Well, we use 24. That'll be fine, 24 degrees. Or we could use, Well, if we use 336, we're going to get a negative number, but that can't be because the friction's in the opposite direction, so it has to be negative. So we're just going to leave it 24, okay, times 2.4 meters. That's a 4, right? Yeah. Or excuse me, not 2.4, 2.8. My bad. Did I put that? Yeah, 2.8. 2.8. 2.8 meters. There we go. And so we get an answer of 55.8 joules. Now, how do you know it's positive, Mr. Shields? Well, okay. I forgot to put my angle in here. We're just going to say 24 degrees right there. All right. We know by physics that the friction has to be in the opposite direction. Since the box is sliding towards the effect of gravity, then it's going to be positive. Okay? Because remember, when we look at work, positive potential energy is when the box is moving towards the effect of gravity. Okay? So it's positive 55.8 joules. All right, so that's the work done by gravity. All right. Then what's the next part? What is the work done on the package by the normal force? Okay, well, let's look at that. So 64C, the work done by the package on the normal force is what? Well, okay, y'all, let's look at it. So the work done by the normal force is equal to what? Well, it's force times distance cosine theta, force times S cosine of theta. So the force then is what? Well, all right, so what is the weight of the object? The weight of the object is, did it give us the mass? Yes, so we'd say 5 times 0, 0.0 kilograms, 0, times 9.8. Times cosine. Hey, now what angle is it going to be? Well, it has to be a 90-degree angle. You know where this is going. Times 2.8. Yeah, that's 0 joules. Say what? Yeah, because the cosine of 90 is what? 0, isn't it? Yeah. And cosine of 90 is 0. Okay? Sure is. Remember, we said there's no work because it's not moving in that direction, y'all. It's not moving in that direction. It's sliding this way. So with relation to the direction it's sliding, that's a 90-degree angle. The cosine of 90 is 0. So there you go, 0. And then we look at what? Oh, me. This is a long one. The total work done on the package. All right, so what would the total work be? Well, that's easy. 64D, work total or work net. Think of work net or work total. You just add them up, y'all. Okay? So we would have 55.8 minus 38.9 or 38.85. I think I used 38.9. And what do you get? You get 55.8 16.95. Yeah. So that's the total work, or the work net. Okay? And then E, goodness gracious. If the package has a speed of 2.2 meters per second at the top, what is its speed after it has slid 2.8 meters down the ramp? Oh, my stars. Okay, so let's go to a clean slide. So 64, what was that? 64 E? Yeah, 64E. All right, so, wow. Well, we know then by definition that the work, kinetic energy theory, work is equal to the change in kinetic energy, right? So then that means the work is equal to 1/2 mv squared final minus 1/2 mv squared initial, right? So we can find the final velocity this way. Well, let's do this. Let's solve it for k final. By the way, this is the same as saying k final minus k initial, right? That right there is, okay? So let's write it that way. I should have written it that way. This is k final. This is k initial. So let's solve it for k final. So k final is equal to what? Well, it's the work plus the kinetic energy initial. Okay, so then we have what? We have 1/2 mv squared final is equal to work plus 1/2 mv squared initial. All right? Okay, you with me? Hopefully everybody is. So let's just keep doing some substituting here, and let's do our equation. Okay. Now, we found that the work was 16 point what? There's a couple of different ways you could actually do this. You could go ahead and find the initial kinetic energy, because it gave us a speed. The initial speed was 2.2 meters, and the final displacement change in x is equal to 2.80 meters. Okay, so you can do this a couple of different ways. You could go ahead and solve for the initial, and it would make the equation a little bit easier, because y'all, we've already found the work net, which is 16.95. So you could do it that way, or you can just go ahead and do all this crazy, ungodly arithmetic and solve it this way, okay? I don't know which way I want to work it. I could come in here and solve for, what's it asking for? The final velocity, right? What is the speed after slid? 2.8 meters, yeah. So I could work it that way, or I could work it the other way. I'm going to work it the other way. So let's do it this way. We already know K final is equal to the work is 16.95. We've already found that, joules. Now let's find the initial. Well, okay, y'all, 1/2 times 5 kilograms times 2.2 meters per second squared. And then that comes out to be this. K final is equal to 16.95 joules plus 12.1 joules. That comes out to be 12.1. And we get what? 29, yeah, 16.95 plus 12.1 is 29.05 joules. Okay, so 29.05 joules. Now we can find this is saying 1/2 mv squared is equal to the work, because that's the total work. Okay, yeah, is equal to all of this, 29.05. And like I said, we could go up here and solve it, but I'm going to do it this way. I did it this way. So then and that's the final, and so then the final velocity is equal to the square root of 2 times 29.2 times 29.05 joules divided by 5 kilograms. And you get an answer of 3.41 meters per second. Okay. So that's the final velocity. All right. Okay, that one's kind of long, isn't it? Okay, let's look at number 66. I'm about to get a little tired, but anyway. All right, we got a net force. This is on page 197. We have a net force along the x-axis has an x component of, and so we've got a net force. So we've got an object here that's moving along the x-axis. This is x and that's y. Okay. All right. And the force applied to it. Okay. Force applied to it is this function right here. F of x is equal to negative 12.0 newtons. That's a negative. Plus 0.300 Newton meters squared, newtons per meter squared, x squared. And that force is applied to the 5 kilogram object, so the mass is 5 kilograms. Okay. That is initially at the origin and is moving in the negative x direction with a speed of, it's initially at the, and so it's moving in the negative x direction. So it's actually backing up. Moving that way. Okay. All right, so it's moving there with a speed of, so the speed is 6.00 meters per second. What is the speed of the object when it reaches a point x is equal to 5 meters? So the speed is moving in the, all right, the force, all right, I think I wrote that wrong. Well, it says negative, so okay, we're going to leave it like that. So what is the speed of the object when it reaches a point of x is equal to 5 meters? So x final is equal to 5 meters. We want to know what the, that's the initial, we want to know what the final velocity is, question mark, right? Okay. So we want to know what it is. Well, how in the world are we going to find that? Well, you can't forget your work kinetic energy theorem. We know this. We also know that work is the integral of the force dx, right? We sure do. So how in the world are we going to work this? Well, we're going to have to integrate, y'all. We're going to have to integrate. So all right, let me look at my notes just a second. Oh yeah, and it does start at initial of 0, x initial. I forgot that, 0 meters, okay? So it says, read it again, what is the speed of the object when it reaches a point of x is equal to 5 meters? Well, the first thing we got to do is determine how much work we have, okay? That's the first thing we got to do. So we got a function, y'all, we got to integrate it. We can't use this. I know it gave us a speed here, all right, but we don't know how much work, okay? So see, I can't use this equation because I don't know how much work. But I can use I can integrate because I'm given a function, and notice it's x squared. So we're going to say the work is equal to the integral of 5 to 0, and that is what? We're taking the integral of what? We are integrating, well, let me write it this way. Five to 0, and that is 12 newtons plus 0.300 newtons meters squared x squared. So when we integrate this, we got 5 and 0. Then it becomes what? We can pull the work out, we can pull the force out. Let me do this. 12 newtons, 5 and 0. So when we integrate, that becomes what? That becomes 0.300 x cubed over 3. Okay? So let's plug everything in, and that's a negative 12, by the way. So we have a negative 12 newtons times what? If you divide that through, that becomes 0.1, so that's negative 12 times 0.1 Newton meters squared x cubed. And so now let's plug everything in. Let's plug in our distance, okay? So we have work is equal to 12 newtons, negative 12 newtons, times 5 meters, plus 0 point, because you say, where are you getting that? Right here, y'all, right here. I got to multiply times my distance right here, okay? Look at the function there. If you make that work, you got to multiply it times your distance. There's your distance. Times 0. Oh man, 0.1 newtons meters squared times 5 meters cubed. And what we wind up with is we get a negative 60 joules minus 12.5, no, excuse me, plus 12.5 joules. And we get a work of negative 47.5 joules, okay? Okay. All right. I hope that makes sense. Now, again, I know some of you are saying, why'd you multiply times 5 right here? Because force times distance is work. Force times distance is work, okay? And that's why. All right? Now, okay? And I didn't do the 0 part of that integration because 0 times 0 times whatever is 0, okay? So now we have the work. So now we've got to do what? We've got to find the speed of the object when it's at 5 meters, okay? What is the speed of the object when it reaches 5 meters? Oh, Lord, how do we do that? Well, okay, we go to our work connect. So we got our negative 47.5. So we know this is 66, yeah. So we know that work is equal to the change in kinetic energy, which is the same as saying work is equal to K final minus K initial. We just did a problem like this, so we want to find K final. So K final is equal to what? Work plus K initial. So we have 1/2 mv squared is equal to, come on now, the work plus, and that's final, plus 1/2 mv squared initial. Okay? Do all the arithmetic. And by the way, our work is negative there because we got a negative answer. All right, 1 second. I'm double checking my mathematics here. Yeah. So when we solve for V final, we get this right here. Under the radical, V squared initial, V initial squared, minus 2 times the work over the mass. So we got the square root of, the initial velocity was 6 meters per second, it told us that. let's see now. That's hang on a minute. I'm gonna double check something here. Let me pause a minute. Okay, yeah. So it's minus, and we've got 2 times 47.5 divided by 5 kilograms. And that's all under the radical. Now where'd that negative go? It's right there. It's right here. See, actually, this should have been negative because I got a negative answer for the work. Okay? And you should get 4.12. So let's double check that. 4.12 meters per second. Okay? So you got 47.5 times 2 divided by 5 is 19. So 36 minus 19 is 17. And the square root of 17 should be 4.12. Okay, that's right. So you don't let that negative say, oh, you can't have a negative on the radical. Wait till you get done. You do everything under here first and then take square root. Okay, 4.12 meters per second. Wow, what a problem. A lot of work in that one. All right, we got one more. Number 68. And this is still on page this is on 197 now. Did I put that on that other one? This is on page 197. Yeah, I did. All right. Consider a spring that does not obey Hooke's law very faithfully. One end of the spring is fixed to keep the spring stretched or compressed an amount of X, a force along the X-axis with an X component of, and it tells you the X component. Okay, so here they're doing it in a horizontal fashion, which I really don't like doing, but we can do that. So we got a spring here attached. Okay, and it says that the spring that does not obey Hooke's law very faithfully, one end of the spring is fixed to keep the spring stretched or compressed amount X. They force along the X-axis with the X component being this. So the force in the X direction is Kx minus Bx squared plus Cx cubed. Okay. Must be applied to the free end. Hence, K is 100 newtons per meter. So we got to write this down. So K is 100 newtons per meter. B is equal to 700 newtons per meter squared. And C is 12,000 newtons per meters cubed. Note that X is greater than 0 when the spring is stretched. So when it goes this way, X is greater than 0, and when it's going that way, X is less than 0, okay? In other words, it's negative. All right. How much work must be done to stretch the spring by 5 centimeters, 0.05 meters? So this is 68A, so we want to know how much work to get it to 0.5 meters, question mark, okay, from its unstretched length. So how much work does that take? Well, all right, y'all, we've got a function there. We got force and we got X, force times X, but that's a function. So we know then that work, and if it's a non-constant force, is the integral of force dx. So, y'all, let's integrate the sucker, all right? So we're going to come in here. So we're going to say work is equal to the integral of 0.05 to 0, and that is kx minus bx squared plus cx cubed dx with respect to x, right? Okay, So when we start integrating everything, it looks like this. We got the work is equal to 0.05 and 0. And see, we're not going to need to do the final minus initial. We're not going to need to do that one because it's 0. 0 times whatever is 0. Okay? So I'm not going to show you that part. Don't need to because it's 0. So we do what? Well, when we integrate kx, it becomes kx squared over 2. When we integrate, that's a negative, by the way, bx, it becomes bx squared, it becomes bx cubed over 3. And when we integrate cx cubed, it becomes cx to the 4th over 4, right? Okay, now let's just start plugging everything in. All right, let's just, plug and chug, or chug and plug, or whatever you want to do. So the work is equal to, and we've got that 0.05 to 0. The K was what? 100. So we got 100 newtons per meter. Okay, times what? X is 0.05 squared over 2. And by the way, if you want to go ahead and divide that out and make that 50, you can. That's okay, but you don't have to. Either way, minus what was B. All right, B is 700 newtons per meter squared times 0.05 meters, and that's what? And that's meters, and that's what? Cubed? Yeah. Cubed over 3. Plus, then we got 12,000 newtons per meter cubed times 0.05 to the 4th over 4. And like I said, you can divide these in here and get rid of that fraction there on the bottom if you want to, or just go ahead and work it this way. Either way, it doesn't matter. And so what you should come out with is you should come out with a work of 0.115 joules, or very close to that, okay, when you do all that in there. Well, where's the, okay, look, I'm going to keep you folks happy, 0 minus 0. Because when you put 0 in for every one of those x's, everything becomes 0, okay? All right, so it's positive work. And that makes sense because you're stretching it in the positive x direction, okay? All right, now let's look at B. Let's look at B. Now let's go to the next page. 68B. It says to compress this spring by 0.05 meters from its unstretched length. Okay. All right, well, you're going to use the same equation that we've already discovered. Go back. You're going to use that right there. The only thing that's going to be different is now it's negative. So now we're going to integrate it like this. It's going to be a negative 0.05 to 0. Well, how do you know it's negative? Well, back up and look. All right. If this is the 0 starting point, and then you come out here to 0.05 meters, well, then you've got to do what? You got to go back that way, and that's in the negative x, so that's a negative 0.05 meters. Okay. All right. Okay. So let's see. What was that? That's kx squared over 2. Yeah. So that's going to be kx squared over 2 minus bx cubed over 3 plus cx to the 4th over 4. So now let's plug everything in. That's a negative. Integrating 0. All right, so K was 100 newtons per meter times a negative 0.05 meters squared over 2 minus, and this was 700, I think. So 700 newtons per meter squared times a negative 0.05 meters cubed over 3. And this is plus, and this is 12,000 newtons per meters cubed times 0.05, negative 4, and then over 4. Okay, don't forget your negative on that now, all right? Well, when you square a negative, it becomes positive. When you cube a negative, it's negative. When you quadruple a negative, it's positive, okay? So notice how that's going to change everything. It's going to change it considerably, because then the work comes out to be what? Then our work, notice, is 0.0173 joules. So notice that it takes more work to compress it than it does to stretch it. Okay? It takes more work to compress it than it does to stretch it. If you've ever compressed a spring, that makes perfect sense. Okay? If you just think about it. Now let's look at the next part. Is it easier to stretch or compress the spring? Explain why in terms of the dependence of the force on X. Okay? All right, so how in the world, y'all, are we going to find that? Well, how are we going to find it? Okay, we got the work. We found the work to stretch or compress, okay? Well, let's go back to our function, okay? Let's go back to our function and let's work it. You say, what do you mean? All right, well, let's go back. All right, remember, come on, computer. Remember that this is 68. Oh, is this C? 68C? Yeah. Okay. Remember that Hooke's law says this right here, right? Kx. Okay. All right. So let's look at our function. So we had a function that was like this. F of x is equal to bx squared minus bx minus cx squared plus, I can't even remember the crazy function. I'm about tired. I've worked so many problems today. Start over. My apologies. Kx minus bx squared plus cx cubed. There we go. So now let's just plug in everything for 0.05 meters, positive. Okay, well, plug it in. You got 100 newtons per meter times what? It's positive now, 0.05 meters, minus, what was that? 700 newtons per meter squared times 0.05 meters plus 12,000 newtons per meters cubed times 0. And that's squared, and this is what? 0.05 meters cubed. And y'all, when you do all of that, you get 4.75 newtons. So it took, to stretch it 0.5 meters, it took 4.75 newtons to stretch it. That's to stretch, okay? To stretch it. Now you do the same thing for the negative, okay? Well, look, you just come in here and say force is equal to negative 0.05 meters. Remember, you're going in the negative x direction, so it has to be negative. Remember, you've got to remember your inertial reference frame. Where did the motion start? Well, it started at 0, so if I'm going to the left of 0, it's got to be negative. Hello, you got to remember that now. You cannot forget that inertial reference frame. Where did you begin motion? Well, I started at 0. Well, if I go to the left of 0, that's negative. That's why it's negative 0.05 meters. All right, and then just plug everything in. So you got 100 newtons per meter times negative 0.05 meters minus, now see, here's where it's going to get important, minus 700 newtons per meter squared times a negative 0.05 meters squared plus 12,000 newtons per meters cubed times a negative 0.05 meters cubed. Okay? All right? And then you get an answer of negative 8.25. So the force to move it in the negative direction to compress the spring is negative 8.25 newtons. Negative 8, that's to compress the spring. Okay? Well, y'all, there's my proof. Okay, it took more work to compress it than it did to stretch it. And there's my proof. It took twice as much force almost twice as much force in the negative direction. Okay? All right, I hope working all these problems helps out.